Okay, so last time we excuse me, we were talking about several things, including we talked about the periodic table. We talked obviously about where groups are on the periodic table, again going up and down. Remember, again, we do use the representative numbering, and that's sometimes referred to as the A numbering there. And that means group one is with lithium, and then group two is beryllium. We do skip the middle section, which is our transition metals. We pick it back up with group three, which is boron and carbon, 4, 5, 6, 7, and 8, down to where our noble gases are, helium. Again, you also need to know, obviously, some of the those group names, the specific names, like the alkali metals, which are group one, the alkaline earth metals, which are group two, the halogens, which is group 7, and our noble gases, which is group number 8. Also, where metals are on the periodic table, again, essentially from sort of that staircase to the left are our metals. Where that staircase is kind of going up and to the right of the periodic table. That's our nonmetals in that staircase, which is around boron, silicon, all that kind of guys there. Those are our semi-metals, or our metalloids. And again, those are elements that basically have properties that fall, between both a metal and a non-metal. So the same element, for example, has some properties that would be considered kind of metal-like properties, while the exact same element would also have some properties that are considered more non-metal in nature. And it does sort of make sense, since we are, kind of going from left to right on the periodic table and building up to that upper right corner of the periodic table, going from metals to non-metals. That staircase, sort of the transitionary point between metals and non-metals. So it does sort of make sense that those guys on that staircase do have properties that are kind of fall on both sides, ones that are similar to metals and ones that are similar to obviously non-metals. Also, we talked about the lanthanides and actinides, which are on the bottom, although we don't really deal too much with those guys. A reminder that, again, if you follow the atomic number, we're looking at really those guys following the 57 and 89 there on the main group. And that is why they're also sometimes, as we talked about, referred to as inner transition metals. So sort of where we left off, and sort of the last little bit here of this chapter, we're going to talk actually about some periodic trends. These periodic trends, obviously from the periodic table. And we're going to talk about 4 sort of main trends. One is ionization energy. One is electron affinity. One is atomic radius. And one that really is from sort of chapter 3, which is electronegativity. And a reminder that, for our first exam here, that's really the only little bit of chapter 3 that will be on there, is just sort of what electronegativity is and a little bit about the trend. So we'll talk about that. And then obviously we'll get into the real chapter 3, which will pretty much all be on chapter exam 2, the rest of it. So let's talk about then the first sort of trend, which is ionization energy, and sort of what ionization energy is. So ionization energy is essentially the energy that's required to remove an electron from the gas phase of an atom. So it's basically when we remove electrons. And we talked a little bit about this. If we do remove an electron, we're really talking about forming a cation, right? If something loses an electron, it's going to be positively charged from losing those electrons. So really, when we sort of talk about ionization energy, we're sort of talking about, really the formation of a cation in this particular case. Now, if we look at something like magnesium, as we see here, electrons actually do come off pretty much one at a time. So they don't come off all at once. So although we think about sort of magnesium as always having a +2 charge, it actually, the electrons are removed one at a time. So if we just look sort of at the electron configuration for magnesium before we start, 1s2, 2s2, 2p6, 3s2 in this case. When magnesium goes through it, the first thing that's going to happen is it's really going to lose one electron. So it's going to lose this one electron right about there. And that's going to be require 735 kilojoules of energy. This is what is sometimes referred to as the first ionization energy. The first ionization energy is the energy really to pop off that first electron. Then what would happen is that magnesium that has lost one electron will then pretty much pop off the second one. And we see that we go to about 1400 or so kilojoules of energy. That is what is sometimes referred to as the second ionization energy. Second ionization energy because it's basically the second electron we're going to pop off. And then that magnesium with a +2, if you wanted to try to pop off that third electron, we're going to end up with a third ionization energy of 7,730. So does that really occur? Doesn't really occur here with magnesium. A couple of things that we do see if we look at sort of this trend is we see that as we go from the first electron, about 735 kilojoules of energy, to the second electron, we almost double the energy, which means it's much harder once we pop off one electron to remove the next one. So why would that be? Well, when we lose an electron, we become smaller, right, than the neutral atom, right? Because you think about, we have our nucleus, we have our electrons. So obviously if we lose an electron, we now have less of an electron cloud. By the way, we also have a higher positive charge than negative charge, and that's just going to bring everybody in closer. And overall, what we see is neutral atom, something that becomes a cation, is significantly smaller because of that. We lose a lot of that electron cloud. The electrons that are there are now going to be kind of brought in closer to the nucleus because the nucleus is now carrying a higher positive charge. And we do see that sort of separation that occurs, or that difference in terms of the size. So once it does that, we then would lose another electron, which, as you can see, it then goes up almost 6 to 7 times the amount of energy that's required to do that. So will that happen? And to sort of answer your question, if I'm reading it correctly, um, you know, the difference between, say, a piece of magnesium with no charge like this guy, it's just like a piece of magnesium metal. Um, just by itself has no charge. It only really gets a charge when it gets near something that, like a nonmetal, for example, that will allow it to sort of lose an electron. And then at that point, what we end up with is sort of magnesium that's now going to be attracted to the nonmetal, for example, chlorine. And now we're going to have some attraction between those guys, the electrostatic attraction that will happen. So probably a good point, just to make sure everybody is sort of on the same page. When we talk about sort of elements there on the periodic table, I'll back up, I think that's somewhere right. Um, you know, when we look at metals or any sort of element just from the periodic table, any element that's really not combined with anything, they have no charge. So if you have like a piece of sodium metal, it has no charge. You got a piece of magnesium metal, it has no charge. Calcium metal, it has no charge. Things really only get charged when they sort of come in contact with, especially metals, they really only get charges when they come in contact or near things like nonmetals. And that's going to sort of initiate those electrons to be transferred, really based on a lot of the trends we're going to be talking about here that's going to cause that to sort of occur. So the other thing is also true is something with no charge has sometimes a lot of different properties per se than something with a charge. If you had a piece of sodium metal, that's just going to be like a solid piece of metal. It's actually very soft as well, but it's going to be like a really solid piece. When like sodium gains a charge, it oftentimes will obviously be with another ion that's negatively charged, And a lot of times these guys with charges actually end up in solutions, and they're more like ions that are a lot of times just kind of floating around in the solution, which you can't really see in a lot of cases, right? So if you just think about salt water, which is sodium chloride, you can't really per se see these sodium ions or chloride ions in most cases, right? Because it's dissolved. Obviously, in the solid state of sodium chloride, you can see the salt crystals. But, a lot of times, if they go in for a swim, they can dissolve, as opposed to, I want to say if you put sodium metal in water, you would be able to see what would happen. It gets very, very reactive, obviously. But, there's some differences when things sort of have charges and when things don't have charges. But an important thing to remember is any sort of element by itself really will not have a charge unless, really a metal and non-metal are sort of coming together to form an ionic compound. So since we're talking about things with charges, let's just talk about the periodic table for a second. We'll back up for just a sec. Everybody in group one, when they do form a charge, will form a +1 charge. Everybody in group two will form a +2 charge. Group three, a +3 charge, pretty much aluminum is what we're talking about there. Here's about where that staircase is. Skipping group four, group five will be -3, and these are the nonmetals above the staircase. -2 in group six for those nonmetals, and -1 for group seven. Again, those nonmetals above the staircase, those nonmetals are the ones that will become negatively charged and gain electrons, while our metals typically will become positively charged from losing electrons. In our transition metal region, pretty much they do have a variety of charges that could occur, but there actually is 3 that have fixed charges in that transition metal region. Zinc and cadmium, pretty much no matter the situation, when they do form a charge, will be +2. If you hang a leftover there at cadmium and go to silver, it will form a +1 charge in that particular case. So again, things don't always have charges unless they're pretty much combined with something, but these are the common charges, cations and anions, that some of these elements on the periodic table typically will make. So going back to sort of where we were with this and ionization energy, again, is that energy that's required to remove those electrons. So if we talked about valence electrons as well, and when we look at valence electrons, it does equal the group number. And no, there's really no good sort of pattern there for group 4. And that's really because group 4 is right about where, we have the staircase coming down. So kind of above it, we got some nonmetals. Below the staircase, we have some metals. So there's no real good pattern per se for group 4. So we kind of think about it when we think about charges is going, you kind of go group 1, +1, +2, group 3, +3, skip group 4, and then you kind of go backwards, -3, -2, -1, again for those nonmetals up there on top. Now, when we look at those valence electrons in magnesium, which is those outermost electrons and the highest energy levels, remember that these guys, as we were sort of talking about at the end the last time as well, because they're so far away from the nucleus, there's a lot of shielding that's happening. So remember that they are not really feeling that full brunt of that positive charge from the nucleus, which is why they're able to be lost relatively easy. And that's why when we look at the first ionization energy to lose the electron, not a big number. Second one gets a little harder to lose the second one, but still manageable. But at this point, we have now pretty much lost our 2 valence electrons. We are now going to be digging into those core electrons. And those core electrons are obviously at this point going to be much closer to the nucleus. Plus, imagine after you lose that second electron, all the remaining electrons again are going to be pushed in a little bit closer to that nucleus because we're ending up with a much higher positive charge than negative charge. And again, even though now those outer ones, like these guys, even though they kind of started kind of far away, just by the process of losing those 2 electrons, they're moving themselves closer to that positive charge and are going to be held a little bit tighter as well. So that's why we see a very big jump as we go from the second electron to the third electron, because now we're getting into those core electrons. And as the case for magnesium, which is group number 2, it pretty much doesn't happen. So we don't really see that, but we do see that general trend where it gets much, much harder to remove electrons as you keep removing one electron to the next electron as well. Now, in general, when we look in general about the ionization energy, the general trend for ionization energy is it increases as we go this way on the periodic table, and it decreases as we go down on the periodic table. And that makes sense because, again, ionization energy is the energy required to remove an electron. So if you think about kind of this part of the periodic table, that's pretty much where we have all of our metals, right? And those are the guys that typically will lose electrons and become positive charge. As the ionization energy increases, it becomes harder and harder to remove electrons. So if you think about where you'd find the highest ionization energy, that's the upper right of the periodic table where we have our nonmetals. And again, our nonmetals there are our guys that will essentially gain electrons and not really lose electrons. So it takes a tremendous amount of energy even to remove or try to remove those outer electrons. Any questions on ionization energy, the trend there? Also why, and I think we might see a table, but also why, when we lose that sodium ion to make the sodium ion the first electron, again, that is its valence electron, and that can happen. Not a lot of energy required to sort of do that. But, if we try to then get a sodium with a +2 charge, not going to really happen, because at the point for sodium, for example, which is 1s2, 2s2, 2p6, 3s1, once we lose that first electron, that is all the valence electrons it has. And now when we try to remove that second one, we're going to get into those core electrons. So we're not going to be able to really do that. So in general, as we go from across a period from left to right, the first ionization energy increases and it decreases as we go down. And again, some of this is related also to some things we'll talk about. It's related to size. So again, if you just look at the periodic table, as you go to the right, you have a lot more protons, right? So a lot more protons means bigger positive charge. Remember, the attraction of positive and negative increases with increasing charge. So the bigger the positive charge, again, even those outer electrons are going to be pulled in a little bit more than if you go kind of to the left-hand side of the periodic table, where, you got something like lithium that's got 3 protons, it doesn't have as much of a pull to bring those electrons that close in. So as we'll see, is we generally do see sort of smaller atoms as we go to the right and up on the periodic table, and a little larger as we go to the left and down. Here's helium, neon, argon, krypton, and so forth. So if you look at the periodic table, this is going down group 8. And again, we see a decrease in the ionization energy as we go down. Again, that is following that trend of what I was just talking about, increasing up and to the right for ionization energy, decreasing going down. So within a group, we would expect the ionization energy to decrease, and that's what we see here. Again, this is basically group 8 on the periodic table. We do see that decrease. We also see sort of that decrease as well if we go next door there. There's kind of fluorine, chlorine, bromine, and so forth coming across that way as well. So we kind of see that decrease in ionization energy. So explain why the graph of ionization energy versus atomic number is not linear. Where are the exceptions? Well, there is going to be some places where we do get some electron repulsion. You don't have to worry specifically where there's certain those exceptions. But much like a lot of trends, nothing is perfect. So that's why a lot of times we talk about sort of periodic trends as sort of general trends. But the general trend is, when we go up and to the right, our ionization energy is going to be increasing and decreasing left and down. So take a second here. Which one would require more energy to remove an electron? So would it be sodium or chlorine in this case? So hopefully all you pretty much need to do is kind of look on the periodic table in this deal and just really look at those locations. And if we look at the locations, we have sodium kind of on this side, we got chlorine on this side, and the energy to remove an electron is the ionization energy. And again, it increases as we go this way, which means chlorine should be the one that would require more energy to remove it, not as much energy obviously required here for our sodium. Any questions on that one there? All right, take a second here and see what you come up with on this one. Which atom would require more energy to remove an electron? Is it lithium or cesium? So I see some answers coming in, so I'm thinking we're doing good on that. So again, if we just kind of look at the periodic table and there are locations, in this case, they're actually in the same group. So we got like lithium here, or we got like, what we got there? Cesium, right there. So again, the general trend for not electronegative, ionization energy is it does decrease as we go down a group. So this guy here would require less energy than lithium. So the question wants to know which one is more energy to remove an electron, and it would be lithium. Also, it does relate a little bit to size as well. And as we'll talk about when we go sort of down on the periodic table in terms of size, when we go up and to the right, the overall size of the atom gets smaller. And when we go kind of left and down, the overall size gets larger. So what that means is when we're talking about a lithium atom over here, say, versus a cesium atom over here, the overall size difference, there's sort of an overall size difference that's occurring. So the lithium is going to be smaller than, say, the cesium. Not drawn to scale, obviously, but just in the fact that it is sort of smaller, that means those outer electrons, even though they're further away, are now going to be really closer to that nucleus than, say, the outer electrons here in our larger cesium, which has a bigger electron cloud. Again, just by pure distance and some shielding, this guy is going to feel more shielding, not going to feel as much of this positive charge, and going to allow it to be popped off a little bit easier than, even though this guy also is the outer electron, but it's still in proximity wise kind of closer to the nucleus and going to be held a little bit tighter. Which would have the larger second ionization energy, lithium or beryllium? All right, so I see some answers rolling in. So here we're looking for, again, the second ionization energy. So that is basically when the second electron would come off. So let's just kind of take a look at each of these here. If we did our good friend lithium and 1s2, 2s1, if we did beryllium right next door, 1s2, 2s2. Lithium is group 1, which means it has really one valence electron. This is its core electron here, our core electrons. Beryllium, which is group 2, has 2 valence electrons, which are those guys there. And these would be the core electrons. So again, as I mentioned before, if we were getting to the second ionization energy for something like beryllium, the first thing that would happen would be beryllium would become positively charged, lose 1 electron. That would be our first ionization energy. That's a very badly drawn E there. What happened to that E? E. There we go. Then what would happen is our beryllium would then lose its second electron. Try to write IE a little bit better. There we go. Oh, it's still, I don't know. I don't want to, apparently don't want to write the E. So this is what would happen. Now when we get to lithium, it would lose its first electron, which would be our first ionization energy. And then our lithium, if it did this, would go and lose its second electron, which would be its second ionization energy. So clearly I could write the equation for both of those, so perhaps it could happen, but the reason it's not going to really happen is there is a difference here. The difference is even when we get down to here, which is our second ionization energy, we are still taking out our valence electrons. So not a problem. That's not going to be too much of an issue. It is going to be harder than the first electron, but probably can occur. The problem though, when we get to our second ionization energy for lithium, we only have 1 valence electron, which is gone after this step. Now you're going to try to pull out that core electron to remove the second one. Not going to happen in the case of lithium. And that's why it would have a much higher second ionization energy, because again, at that point for lithium, we would be going into the core electrons. Question on that there. So here is a table of ionization energies. And again, basically first, second, all the way to 7, or something that makes a lot of positive charge. But here's our group 1. And the general trend that we see, for example, as we go from, say, sodium, magnesium, aluminum, silicon, phosphorus, sulfur. So this is really period 3 on the periodic table. So if we go to periodic table, period 3, heading in this direction, starting with sodium and kind of ending over there at argon. And as we know, if we go to the right, we would expect to see an increase in the ionization energy, the first ionization energy, and we definitely do see that trend like we talked about. We also see the trend where we go from the first ionization energy to the second, it also increases. And here for sodium, as we were maybe just talking about a second ago, it goes for 495 kilojoules to remove that valence electron to, you got to almost do 10 times that amount of energy to try to rip off a core electron. Not going to happen in that particular case. Again, that's why we always see a sodium with a +1 charge. For magnesium, we go from 735, then you got to double it. But then as we were talking about, then you almost got to go 7 times, which again is because we have now just entered our core electrons. Look at aluminum, we go from 580, gets a little bit harder with aluminum, even harder, and aluminum is +3. And as you can see, if you're trying to take that 4th electron out, good luck to you. It's not going to happen. And again, that's why aluminum will essentially be a +3 charge at best. Why perhaps these guys coming this way don't typically lose electrons? They're starting pretty high to even try to pull off that first one, and it's not going to most likely happen in most cases. And as you can see, it gets increasingly harder if you wanted to try to rip off any of those electrons, and usually obviously does not happen. So again, that's why when we talk about sort of our periodic table, our group 1, again, +1, everybody, you'll never find a sodium with a +2 charge. Everybody in group 2, +2, group 3, +3, which again is originally aluminum. We skip our group 4, and then our group 5, 6, and group 7 on the periodic table. -3, -2, and -1. And again, we're talking about the nonmetals when we go across there. And again, as you can see, with those pretty high ionization energies, those guys are really not going to lose those electrons. They're going to hang on to them. Any questions on ionization energy? Do you have to memorize any of those numbers? You do not. You do need to know the general trend in ionization energy, you also need to know the general trend in the first ionization energy to the second to the third. And you need to know what it is, obviously, but you don't need to obviously know any specific numbers or anything like that. The next sort of trend we're going to talk about is something known as electron affinity. And electron affinity is actually different than electronegativity. So there is a difference between those two, and we'll talk about it. But electron affinity is basically the energy change that occurs when an addition of an electron occurs to an atom. So if you remember, ionization energy that we just talked about is the energy required to remove an electron. When we're talking about electron affinity, it is the energy change associated with somebody gaining an electron. So if you think about if something has an affinity for something, that means it likes it, right? So when we talk about electron affinity, it's like somebody liking an electron, sort of gaining an electron. What does that mean when we gain an electron? Well, we talked about ionization energy really being sort of what is happening when we form a cation that's positively charged. When we talk about electron affinity and somebody gaining an electron, we're talking about really the formation of an anion. When it gains electrons, it becomes obviously negatively charged. That's sort of the formula or the reaction. That's what's happening. Electron gets gained, becomes negative charge in this particular case. In general, the general trend, for example, if we had chlorine plus a couple of electrons makes 2 Cl minuses in this particular case. Again, gaining electrons indicated by electrons on the left-hand side of the arrow, as opposed to what we were just talking about with our ionization energy, losing electrons on the product side or the right-hand side of the sort of reaction there. In general, when we look at electron affinity, it increases as it goes to the right and decreases as it goes down. So also really making sense, right? Our nonmetals, which typically are gaining electrons, it's increasing that way. Metals decreasing, coming that way, which are guys that typically don't hang on to their electrons. The atomic radius, we sort of talked a little bit about it just a second ago. Whoops. And then again, in general, as I mentioned a second ago, as we go from left to right and up on the periodic table, we are seeing the size decrease. So again, the general trend in atomic radius is we're going smaller this way, as I mentioned earlier, and getting larger as we go left and down. And that's because the effective nuclear charge increases. Therefore, the valence electrons are drawn closer to the nucleus, decreasing the size. And again, as I mentioned before, really, if you kind of look to the right on the periodic table, that's sort of where all of our big atomic numbers are, right? So we get sort of this buildup of big positive charge happening in the nucleus. And just by that whole process of having that larger positive charge, even those further electrons are going to be drawn in closer than they would if they were sort of on the left-hand side, kind of a smaller positive charge. Those outer electrons aren't going to be tied as tightly or pulled in as tightly. Again, when you're comparing something with like a +3 charge to something with like a +36 charge, you're going to see a big difference in sort of that pull on those electrons that are out there. We touched upon it a second ago, but just I think we talked about it in terms of the cation. So a reminder that if you have a neutral atom and somebody loses electrons, again, all that electron cloud shrinks. And that's why we typically see that cations are smaller than their neutral counterparts. Opposite is true for our anions. Because they gain electrons, we actually see anions being larger, and that's because they pretty much have a bigger electron cloud and sort of everything spreading out. So that's the general trend in atomic radius. Here's a much prettier picture probably than when I drew there. But again, we do see significant decrease in the overall size as we go to the right. Again, that greater positive charge pulling those outer electrons in closer as opposed to going to the left on the periodic table. Any questions on size, our electron affinity? All right, one last sort of trend that we should include in here is electronegativity. And again, as I mentioned before, this is really out of chapter 3. And electronegativity, as we will talk about again in chapter 3, is basically the ability of an atom to bring electrons towards itself. So it is different than electron affinity. Electron affinity is the energy change that occurs when an electron is added to an atom. Electronegativity is the ability actually of an atom to kind of pull those electrons in towards itself. When we look at the periodic table, the general trend for electronegativity is it increases to the right, decreases as you go down. If you look on the periodic table, our good friend fluorine is the most electronegative atom we have. And you could just think about its location as for why that probably is. And obviously is going to take those electrons to the kind of bring them in towards itself. So how does all these trends we just talked about really sort of relate to kind of what we know happens when we think about elements on the periodic table? We think about metals and nonmetals and stuff like that. If we were to sort of just put in all of our trends together here on the periodic table, I'll draw a really giant periodic table and hope for the best. All right, so if we start with the first thing that we talked about maybe, which is ionization energy. So ionization energy increases as we go this way. Ionization energy decreases as we go down. And again, that's the ability of the energy required to remove an electron. We then have our size, which we have on this picture here. Size decreases as we go this way and increases as we go this way. We then have electron affinity, which again is the energy change when somebody gains an electron, increasing this way. Electron affinity. Decreasing as we go down. And lastly, adding in there our electronegativity that we just talked about. Increasing this way with our electronegativity. And decreasing coming down this way. So what do all these trends really tell us? Well, it tells us that if we decide to go up and to the right on the periodic table, up here to the right on the periodic table, heading in sort of this upward and right direction, we have things that have very high ionization energy, which means it takes a lot of energy to remove an electron. We have things that are very small, which means all those electrons, even the furthest out electrons, are going to find themselves closer to the nucleus and actually be held tighter. We have things that have a very high electron affinity, which means they actually like electrons. And they have things that have very high electronegativity, which means not only do they kind of like electrons, they actually want electrons to come towards themselves. So all four of these trends do agree with what we know, which is on the right and top of the periodic table. That is where we find nonmetals, and nonmetals are typically our guys that will gain electrons. The opposite is true if we go kind of to the left and down on the periodic table, staying on the periodic table, obviously. If we go left and down on the periodic table, we have a decrease in ionization energy, which means it does not take a lot of energy to remove an electron. We have an increase in size, which means our atom is larger, which means those electrons are going to be further away from the nucleus, not held as tightly. We also have things that have very low electron affinity, which means they don't really like electrons all that much. And they have very low electronegativity, which means not only they're not really interested in gaining electrons, they're not really interested in bringing electrons towards themselves. And all four of those trends also agree with what we know about metals is they're typically the ones that will lose electrons and obviously become positively charged, while our nonmetals are, for all these trends, really the ones that will gain electrons, bring electrons towards themselves, and become negatively charged. Any questions on those trends? You do need to know, obviously, as we talked about, those trends, all those trends, what they are, and again, their actual trends, be able to put things in order or pick which one would be more electronegative, least electronegative, and those type of things. Any questions on any of that there? Okay. So let's take a look at a few here. Which should be the larger atom and why, sodium or chlorine? So again, if we sort of look at the periodic table, we got sodium, and in the same period, we have chlorine. And we know just from our talk that chlorine should be the smaller guy. Sodium should be the larger one. Again, chlorine would also have a greater effective nuclear charge, that greater sort of positive charge that those guys are going to be filling those outer electrons. And that would make our sodium the larger atom of the two there. Very good. Very good. Maybe come here. There we go. Which should be the larger atom? In this case, it should be lithium or cesium. And based on our conversation, again, I believe it should be, and I agree with you, it should be cesium, right? Again, if we just kind of look at location and understand those trends we were talking about, just very simply, it is further down, which means it should be larger. Also means not going to be hanging onto those electrons as strongly as well. All right. So why don't you think about this one here, or these two? Which is larger? Is it the hydrogen 1s orbital, the lithium 1s orbital, and which one is lower in energy? Is it the hydrogen 1s orbital or the lithium 1s orbital? So take a second and think about both of those and think about what you think the answer might be. Same. And they're really not. So the idea here is which one is larger, the hydrogen 1s orbital or the lithium 1s orbital. So it does has to do with sort of what we've been talking about. So a reminder that, when we talked about sort of the effective nuclear charge, the effective nuclear charge is sort of the positive charge that those electrons feel as a result of, the protons in the nucleus and the electrons that are ahead of it. And again, a reminder, when we talk about effective nuclear charge, Z effective, it does sort of increase as we go this way on the periodic table and decrease on that way. again, as we've been talking about, sort of if you come this way on the periodic table, you're getting that real buildup in protons, right? The atomic number starts to increase. So you get that greater positive charge, and those electrons really do feel, even though they're further out, there's a lot more positive charge, so it's going to bring them in. So if we just compare, say, the hydrogen atom, which has a 1 proton, and we compare something like lithium, which has 3 protons, and we compare our electrons in our 1s sort of situation, as we talked about, the attraction between positive and negative things, the attraction increases with the charge size. So what that means is, although there is attraction here between the electron and that positive 1, what we're going to see on the right-hand side with our lithium is, because of that positive charge that's greater, it's actually going to pull that whole 1s orbital in a lot closer. So because it pulled it in a lot closer, the 1s orbital actually for our hydrogen will actually be larger in that case, because again, the orbital itself is not being tugged in closer to the nucleus as much in the hydrogen than it is in the lithium, because again, the hydrogen only has sort of a +1 charge versus the lithium that has a +3 charge. Any questions on that one there? Now, which one is lower in energy? And again, you may think about it, wait, they're both 1s orbitals. So, shouldn't my 1s orbital, that's, we'll just call this my 1s orbital line here, and my 1s orbital line, be pretty equal to my nucleus? And it's the same idea in terms of the energy and the idea that we were just talking about in the first part. Because if this was our lithium, this is a +3, it is going to drag that orbital in closer than our hydrogen that's +1 in this case, not going to drag it in as far. That means because this orbital will be dragged in by that positive charge, it will find itself actually lower in energy than this 1s orbital that we find in hydrogen. So actually, because of that effective nuclear charge, the lithium 1s orbital would find itself closer to the nucleus than the hydrogen one. Any questions on that there? Okay, here, do that. All right, arrange the elements, oxygen, fluorine, sulfur, according to increasing ionization energy and atomic size. So put those guys in order. Sulfur underneath oxygen in this case. So ionization energy increases to the right, decreases coming down. So that means that we would probably we want to do an increasing ionization energy. So sulfur, which is below both of them, would be the lowest, followed by oxygen, followed by fluorine. So kind of our own trend is going up and to the right, increasing. And that's
can you say why sulfur was at the bottom again?
Yeah, so the general trend for ionization energy is, as you go to the left and down on the periodic table, ionization energy decreases. So if we just kind of just isolate those 3 guys, basically to the left and down is sulfur, right? And that's why it would be the lowest in ionization energy. And fluorine is basically up and to the right, which is what we see on increase in ionization energy. So in this arrangement here, fluorine would be the highest. Other questions on that?
Thank you.
You're welcome. Okay, atomic size. So we could kind of use our general trend for that to help us with it as well. Again, as we talked about, atomic size gets smaller as we go up and to the right, larger as we go down and to the left. So again, if we just sort of rearrange our guys in that sort of situation, and we're getting larger as we go this way, basically. So our fluorine would technically be our smallest, our oxygen would be our next, and our sulfur would be our last one there. Any questions on that? So again, you do need to know these trends and, you know, be able to answer sort of questions like this one here as well. Any questions on those trends? All right, so just to kind of wrap up some of this stuff we've talked about, and I think we've covered most of this here and maybe some earlier slides as well. The number and type of valence electrons is really what determines the atom's chemistry. Those valence electrons, which are the highest energy level electrons, as I might have mentioned before, you know, if you just think about those electrons on the outside, they're pretty much the first guys to say hello to each other when a couple of atoms come together. So they're obviously involved in pretty much chemical reactions and stuff like that. So, and they're the furthest away from the nucleus, or they're not as held as tightly as those core electrons. So they play a significant part, obviously, in bonding and how we form certain compounds. Electron configuration can be determined by the periodic table. We talked about where our D group is, our S group, our P group, and our F group. Again, as we talked about, probably a better idea to do the zigzag guy there that we learned in terms of electron configuration. But I think we also talked about that you literally can, if you know what you're doing, kind of count off electron configuration from the periodic table. Again, the period number would be the quantum number, the principal quantum number, except again that D start on 3 instead of they're on the 4th one, and F start on 4, and even though they're on the 6th period on the periodic table. There's our special names, and remember again, this is our S block here, the 2 electrons. The P blocks is here. This is our D block here, and obviously this is our F block here on the periodic table. And again, a reminder that the period numbers is what we could use to help us sort of count it off. But the key things we talked about, that's 3D there, and that's 4F there if you're going to count electron configuration. Obviously, as we also talked about, knowing these names and where they are located. And I think I mentioned it a bunch of times, but again, group 1 is lithium. Hydrogen, even though on every periodic table you ever see is sitting right there, it is also a non-metal like we talked about and not part of group 1. So keep that in mind as well. We also talked about, again, that location where we find our metals, non-metals, and metalloids. Obviously, you do need to know where those guys are. And, you know, we added to this that kind of +1, +2, again, +3, which is kind of our aluminum there. As we were talking about before in sort of an earlier question, you can see right there in group 4, we got a lot. We got like a non-metal, we got some metalloids, we have some metals below this staircase. So again, there's really no good sort of pattern. You know, you got kind of negative up on top, positive on the bottom, but going backwards here in our non-metal region, -3, -2, -1 in terms of our non-metals when they do make charges. And again, here, zinc, which is here, has a fixed charge of +2 when it makes a charge. Cadmium also a fixed charge of +2. Silver a +1 fixed charge happening in that location. Also, we talked about last time that these 2 guys are sometimes referred to as the intertransition metals as they technically go, you know, in that location there. Any questions on that there? All right, and just to finish up this chapter, talking about just one of those groups a little bit more, again, our lithium, our sodium, our potassium, or rubidium. They are very chemically reactive. They react very violently. If you ever done, I don't know if you've done sodium in water or potassium in water. Years ago at a school I taught at, they let the students throw potassium in water in the laboratory. So if you've never done that, it does actually very, very violently react with water to the point where it oftentimes will catch on fire so much. And again, our general sort of trends in terms of group 1 there is ionization energy decreases, the size gets larger, density increases, melting and boiling points start to decrease. So one last point before we wrap this chapter about those trends and in terms of reactivity, you know, really based on all of our trends, as we talked about, as we go up and to the right on the periodic table, that is where we would expect to find things that would gain electrons, become negatively charged. So that's our nonmetals, obviously. And in the upper right of the periodic table is where we would expect to find the most reactive nonmetal, as opposed to all those trends that helped us kind of end up in this part of the periodic table, where we have things that typically will lose electrons, give up electrons, become positively charged. That's really where our metals are. This is typically where we find our most reactive metal sort of found. So the most reactive nonmetal usually found, again, based off of those periodic trends, upper right of the periodic table, and our most reactive metal is typically found on the lower left of the periodic table, again, because of all those periodic trends. And I believe that wraps up chapter 2. Any questions on any of the trends that we talked about or anything here from this chapter? At this point right here, that is, I believe, all of exam 1 information. So that concludes really exam 1 information, which is really chapters 1 and 2. Again, out of chapter 3, what you need to know is electronegativity. You need to know what it is, and you need to know the general trend and related to obviously the trends we've been talking about. We're going to talk about electronegativity more in the next chapter, but again, it will not be part of exam 1. It'll be on exam 2. And don't ask me when the exam is, but I wanted to say it's like a week and a half maybe or so, I think. So it's not next week, but I think it's the following week, if I'm not mistaken. I'll double check the syllabus, but I teach 4 classes, but I think that's what I have in my head as to when it's at. Thank you. So that's not next week, it's the following week, I think, right? So I think that's about right. That sounds about right. All right, any questions on chapter 2 here? Okay, then we're going to roll into chapter 3. So again, at this point, what we are talking about is not on the next exam. This is exam 2 stuff we're talking about right now. So this would be exam 2 info. Okay, then let us talk about chapter 3. We're going to be talking about, as it says there, covalent bonding, but we're going to be talking about bonding in general, all types of bonding, ionic bonding, covalent bonding. And there is sort of a difference between those two. An ionic bond, as we will see in this chapter, is between a metal and a nonmetal. There's no sharing of electrons. There's a transfer of electrons that occur. And it results in a cation, which is positively charged, and an anion, which is negatively charged. And it is that electrostatic attraction that basically holds an ionic bond together. And that's different, as we will see in this chapter, than a covalent bond. A covalent bond is typically between 2 nonmetals. And the major difference here is we do actually have sharing of electrons. Now, those electrons may be shared equally, they may be shared unequally, which we'll talk about in this chapter, but there's some aspect of sharing of electrons that is occurring when we're talking about a covalent bond, sometimes referred to sort of as a molecular compound. So let's talk about how we sometimes can represent these guys, and we can represent these guys with what is known as Lewis dot symbols. Sometimes they are referred to as just straight electron dot symbols. So what is a Lewis dot symbol? Well, when we do form a bond, as we've been talking about, it really is those valence electrons that are involved. So pretty much all bonding that we're going to talk about in this chapter, and pretty much most of the sort of chemical bonding that you talk about, it really all revolves around those valence electrons. And as we talked about, those valence electrons are the highest in energy electrons. And as we talked about with those trends and so forth, they really are the ones we find not being held as tightly in the atom and easily removed or shared in certain situations. And these are the guys that um, typically are involved in bonding. How can we figure out the valence electrons? So we talked a couple of different ways you could do it. One way is obviously you could write out the electron configuration and just look at it and see which one is the highest in energy. The easier way, right, to remember or figure out valence electrons is it is equal to the group number. So the number of valence electrons in an atom is basically equal to the group number. And that means basically everybody in group 1 has 1 valence electron, everybody in group 2 has 2, and so forth going across. The ones we don't really sort of have to worry about too often, if any point in terms of Lewis dot symbols or electron dot symbols, are transition metals. So we don't usually have to worry too much about transition metals in terms of showing bonding and stuff like that. But our representative elements are groups 1 through 8 equals to group numbers are valence electrons. So what is a Lewis dot symbol? Well, it's very simply the symbol and 1 dot to represent each of the valence electrons that there are. So we don't represent all the electrons when we draw a Lewis dot symbol. Those dots do represent just the valence electrons. And that's important because it really is just those valence electrons involved in bonding. So that's what's being represented when we do those Lewis dot symbols. Here's one I made when I was bored. I really should get a hobby, but again, here you can see everybody here in group 1 has 1 dot, 2 dots, 3 dots for valence electrons, 4, 5, 6, 7, and 8 dots coming across here. 8 is a magic number there in bonding, as we'll talk about in this chapter, is the same number of valence electrons as the noble gases. And almost the basis of all bonding is for people to achieve this noble gas configuration, basically end up with the same electron configuration as the noble gases. So basically, as you can see there, we use the symbol. Is there a hard and fast rule? There's not really how you sort of put the dots on there. The only real rule is usually there's no more than 2 dots per side. Most of the time, people will kind of put 1 dot and then come back and kind of pair them up. And as you can see, 2 dots per side gives you a grand total of max 2, 4, 6, and 8 electrons. So that's the general way people do it. Again, the only real thing is maybe not more than 2 dots, obviously, on one side of the symbol. You may be wondering, hey, what about helium here? He's only got 2, but he's a member of group 8. You do have to remember that helium has an electron configuration of 1s2, which means it's only got 2 electrons, so it can't have 8. So that's why, again, helium here actually only has 2 because of that. It's all it's got. And that's why, even though it's part of group 8, it is an exception in that sense that it actually does only have 2 valence electrons happening. So what about our valence electrons, again, with, say, our transition metals? So again, we really don't deal too much in terms of bonding with anybody in this region, but you will get maybe sometimes a variety of answers from people depending on sort of how they look at things. A lot of people will say that transition metals have 2 valence electrons because, as we talked about, when transition metals lose electrons, they typically always lose those s electrons first, right? And that's 2. So a lot of times people will say that. Some people will say, wait a second, but if I need to lose more than 2 electrons, which transition metals can often do, I then go into the d electrons over here. So if we think about our d electrons, there are some guys in here that have a grand total of 10 d electrons, right? So, I've seen people say, they could have upwards of 12 valence electrons, depending on who you're at, even though they probably won't lose all of them. And some will say 2, and you might even have some in the middle and stuff like that. So me personally, because truly what happens is they do lose these first. And in most cases, those s electrons are higher in energy to begin with. Those are probably the right answer, or I won't say the right answer, an acceptable answer for how many valence electrons a transition metal has. but it's not unheard of, and I've seen people say 12 because of that reason, that they have it. The good news is, really, in this class and most chemistry classes, you don't have to even worry about that, because you're not going to really do much, if anything at all, with those transition metals in terms of bonding. So that's sort of the good news on that part. Just to let you know, again, some would say 12 and some would say 2. I would probably be leaning more towards 2 myself. Any questions on that there? Okay, so as I mentioned a second ago, we're really going to sort of use Lewis dot symbols, or electron dot symbols, to really help us understand, what is happening with all types of bonding. And as I mentioned just a second ago, there really is the 2 types of bonds that we will come across. Again, our ionic bond, and a very key thing that sometimes people don't remember or understand, there's absolutely no sharing of electrons here. So again, we have that electron that's being transferred, and that is going to create our positive cation, our negative anion, and our attraction between those two, as opposed to here, where we definitely do have the sharing of electrons. And again, as we'll talk about here, as I mentioned earlier, maybe equal, maybe unequal sharing. One good way to definitely distinguish between these two, especially for our class, is pretty much 100%, I would say. I guess nothing is 100%, 99.999% of the time, that if you're talking about an ionic compound, you're talking about a metal and a non-metal together. So as soon as you could classify those 2 things as being, one thing's a metal and one thing's a non-metal, you pretty much know you're going to have a ionic compound or ionic bond, and you're going to have a transfer between the metal and the non-metal. And to answer your question, I think we're actually going to do an example so you can kind of see what I mean by a transfer of electrons between the metal and the non-metal. So we'll actually use some Lewis dot symbols in just a second to kind of show what's happening in 1 minute here. And it's also usually a fairly safe bet that for our covalent guys, we're talking about 2 nonmetals. So before we sort of show how that happens, why would that happen? So why that would happen deals a lot with what we just finished talking about in terms of our ionic trends. So if you just think about those ionic trends that we just talked about, basically the take-home message of that ionic trends was, if we're heading up and to the right here, where we find our nonmetals, right? These are guys that pretty much loves electrons, right? They want electrons, they keep their electrons, they bring electrons towards themselves. If we think about metals, which for the most part are to the left on the periodic table, these are guys that typically don't like electrons, don't like to keep them, are willing to let them go pretty easily and become positively charged. So one way to answer sort of your question as well is, the reason why we see when a metal and a non-metal comes together, what ends up happening is this guy goes, I want those electrons. This guy goes, sure, no problem, go ahead and take them. They're going to basically grab the electrons, if you want to think about it that way, from the metal, as a result of those differences in those sort of periodic trends. And that's very different than when we get these 2 nonmetals together. So if we were going to put 2 nonmetals together, we're now talking about 2 elements from the periodic table, which are pretty much right about in this area. Which means when we take a nonmetal near a nonmetal, this guy is going to go, I want electrons. This guy is going to go, I want electrons too. So neither one of them are going to go, okay, go ahead, take my electron. And they're not going to allow one to completely sort of lose the electron, the other one basically pick up the electron. The best they're going to do is go, well, I don't really want to give up my electron completely. You don't want to give up my electron completely. This is the exact conversation, by the way, that happens when they're talking to each other. They're like, can we compromise? Can we do something? And they'll go, I know. Why don't we just kind of, you hang on to some electron there between us. I'll hang on to some electrons there between us. And we'll just kind of share them. We're not going to transfer them. So ultimately, that's sort of the conversation for sure that happens, between those two things, is because really we get those nonmetals that are really in the same position on the periodic table. They share very, very similarly all those periodic trends. So that the best that they really can sort of do and arrange is, well, we'll do some type of sharing. And we may get equal sharing, as we'll talk about. There may be some nonmetals when they come together with other nonmetals, as we will see, that will go, all right, I'll share with you, but I'm not happy about it. I'm going to share a little. I'm going to kind of pull the electron towards me a little bit more, but I'll still let you hang on a little bit. But we're going to have unequal sharing. And there's some that are very agreeable where they're like, it's cool. We'll just kind of share equally. And we definitely don't get that sort of agreement when we get metals, which are sort of on the opposite side of the periodic table, coming together with nonmetals on the upper right of the periodic table. We get a situation where the nonmetal is like, well, I'm going to take your electron, and the metal's going to go, well, cool, go ahead, have a good day. I'm okay with that. And that's, again, probably the right conversation that's occurring between those two things, but that's essentially what's happening. And again, the basis of that is, like I said, is those periodic trends that we talked about as to why we do kind of see that occur. Other questions? All right, so what it tells us, some of these general trends and these general rules that we talked about, is, as we mentioned a couple of times, we do expect our metals really to kind of lose those electrons, give up those electrons with not much of a fight, especially when they're near a non-metal. And that's also goes back to what I was talking about earlier, that when we have these things, these elements that are by themselves, they're not combined, there is not that urge for them to give away electrons or accept electrons. And that's why they really don't have charges when they're by themselves in their natural state. It's only when you kind of get these two guys together that you start getting like our non-metal going, I want your electrons. The metal going, all right, I don't want to argue. Go ahead, take my electrons. We're good. And, or we get two non-metals that come together where they both go, I kind of want your electrons. All right, we'll share. So it's only when things really do start to come together with each other that we do actually start to see things either sort of share electrons, start to get charges in the case of ionic compounds. And also why when they're by themselves, they're good. They're just fine the way they are. It's just somebody else comes along and, again, I don't want to say sort of agitates the situation, but sort of induces that situation to occur. Any questions on that there? All right. So hopefully this will also sort of show you what's going on. Let's actually see how we can represent what is happening in an ionic bond using our Lewis dot symbols. So let's say we take lithium and fluoride and we want to put them together to make lithium fluoride. First off, like I said before, even if you're not sure what's going on here, if you look at the periodic table, that is lithium, which is a metal. That is fluoride, which is fluorine, which is a non-metal. And just by the presence of those two things, we know what's going to happen here. We would expect an electron to go from the metal to the non-metal. We would also expect this to be an ionic bond in a compound. So what's happening here? Well, if we look at our lithium, if I get my thing here to move, there we go. Our lithium, if we do an electron configuration for lithium, it is 1s2, 2s1. If we do our fluorine and its electron configuration, which is 9, 1s2, 2s2, 2p5. If we were to draw our Lewis dot symbols for each of these, lithium, which is group 1, would be with 1 dot to represent its 1 valence electron, which would be this guy. That's its valence electron. That guy right there. And we would kind of add it to our fluorine, which is group number 7, which would have 7 valence electrons. And by the way, that is the 7 right here for fluorine. That is the valence electrons. So because of those periodic trends and stuff that we've been talking about, what's going to happen when these guys get near each other is the lithium's going to go, all right, go ahead, take my electron. And it's going to go over here to our fluorine. And lithium, which started at 1s2, 2s1, and fluorine, which started at 1s2, 2s2, 2p5, when lithium loses that electron, it will then become positively charged, which is our cation. It's at that point that it does become a cation. The fluorine will pick up that electron right there and become negatively charged because it picked it up. And we have now formed an ionic bond. So a couple of things about this drawing. These are cations that do have charges. So when you draw these things, you do need to have the charges included. The charges basically represent that there is no sharing of these electrons. There has been a complete transfer of electrons from the lithium to the fluorine. So sometimes people will put brackets around both. Sometimes people will put brackets just around the negative guy. But this is the way we represent an ionic compound such as this by drawing it like so. First off, any questions on that drawing there? So what is actually happening to our lithium? Well, the one electron it just lost is this guy, which means when it comes to the other side and it's Li+, it will have an electron configuration of 1s2. The fluorine has room in its p subshell to pick up that electron from lithium. And what ends up happening with fluorine with a -1 charge, or fluoride, it becomes 1s2, 2s2, 2p6 in terms of its electron configuration. So by the lithium in this case losing an electron, it ended up with an electron configuration of 1s2, which is the same electron configuration as helium on the periodic table. Fluorine gained the electron, which ended up with 10 electrons, which is the same electron configuration on the periodic table as neon. These two guys are noble gases. That means that lithium with a +1 charge is isoelectronic, like we talked about last time with helium. Fluoride with a -1 charge is isoelectronic with neon. And the basis of bonding is this, as we will see over and over again, by losing electrons and gaining electrons. Both of these guys were able to achieve noble gas configuration. And that is, again, the purpose of all bonding is for everybody to end up in the most stable arrangement. And the most stable arrangement is the noble gases. And that's why everybody's ultimate goal in bonding is to end up like everybody in group 8. Everybody's trying to get just like everybody in group 8 and end up at that noble gas configuration. Question on that?